I did a problem with the block sliding down a curve with friction where the curve was this way on the inside of a circle. Now we're on the outside of a circle. There is a problem, very famous problem like this, like a block of ice with no friction, and when does it leave the surface? And so we're going to do something very similar, but we're going to have friction, and it's going to be awesome. There's a whole bunch of cool stuff. We're going to model it in Python. We're going to have a great time, and at the end, everyone's going to be happy. Okay, so let's start off with a force diagram. So I do have something over here. I mentioned this before. I'm going to talk about that in a second. So I have three forces acting on my block. I have the downward gravitational force, mg. I have the normal force, N. And then I have the friction force tangent to the path, F friction. And that's it. If the block is constrained to stay on the surface, or while the block's on the surface, then I have the normal force and the friction force. And then if it leaves the surface, there'll just be gravity. But in both cases, it seems like a good idea to use polar coordinates to describe the situation instead of Cartesian coordinates. Because with polar coordinates, the r value is constant during this part, and I just have one variable, theta. And so that makes it a little bit easier. Also, n is in the r hat direction, and f is in the theta direction. So that's a simpler system. So I have this coordinate system. Now, what makes this a complicated problem is that as this block moves, the normal force changes both direction and magnitude with the speed of the block, and so that changes the friction force. So remember that the magnitude of a friction force is equal to the coefficient of kinetic friction times the magnitude of the normal force. So as the magnitude of this changes, the magnitude of that changes. It's pretty tough. Now, the other important thing is that if we're dealing with polar coordinates, the acceleration vector in polar coordinates is not as trivial as you would think. Because if this would be my theta hat direction, right? Because it's in the direction of increasing theta, and this would be my r hat direction of increasing r. So as the block moves, theta hat and r hat don't also change. So the derivative of theta hat with time and theta hat with time is not constant. It's not zero. So you have to deal with that. And when you do that, you get this expression for the acceleration in polar coordinates. I do have a video on this. I'm probably going to make a new video on this too. But there's my acceleration vector. So in this, as a reminder, just r double dot notation is the second derivative of r with respect to time. R dot right there is the first derivative. And we write that because it looks cool and it's simpler. Okay, let's use the acceleration in the r direction, the acceleration in the theta direction to get two Newton's second law equations. So let's start with the r direction. So I'm going to say F net in the r direction is equal to, okay, what forces do I have? Well, here's my angle theta. With the little geometry, you can see that that's the angle theta too, right? Imagine as theta goes down to 0 down over here, then this would come over to that line, so it would be 0 too. So that's the angle theta. So what forces are in the r direction? Well, I have this normal force right here. So the normal force is pushing in the r direction always. So that's really nice. No components. And then here I have the gravitational force, and I need this side of the component of the gravitational force, which would be the sign, right? So it's going to be in the negative r direction. So it's going to be minus mg sine theta. And that's going to be equal to my mass times acceleration in the r direction, which is this. And I'll go ahead and write that out, r double dot minus r theta dot squared. Now, let's go ahead and apply the constraint, because if it's on the surface, then r is equal to a constant value r, so r dot double dot is 0. The derivative of that would be 0. So I get the following, n minus mg sine theta equals m negative m r theta dot squared. So I'm going to use capital R for the variable r, and I get that. I almost missed the minus sign. And now let's solve for n. Why are we solving for n? There are two reasons. Number one, I need that for the friction force. Number two, I want to use that to find out when the block leaves the surface. So if I solve this for n, I can add that to both sides. I get n equals mg sine theta minus m r theta dot squared. That's important. Okay. I'm going to write it right here while I have the diagram. Let's do my Fnet theta direction. Just the forces, and then I'll write it as an equation. So what forces act in the theta direction? So as theta increases this way, theta hat is that way. So the friction force is actually in the positive theta direction. So it's going to be F friction. And then I have a component of the gravitational force right here. So it's going to be minus mg cosine theta. And that's going to be equal to this. So I'm going to say F friction, F friction minus mg cosine theta equals this, mass times that. So it's going to be mass times 2 r dot theta dot plus r theta double dot. And again, r dot is 0 on the surface. So now I can use this to put in for that, and then put this in for that. So it's like a double whammy substitution. So let's do that. Okay. So I have that. I'm gonna I wanna let's just put this in. So I'm gonna put in F friction as mu times n. So it's gonna be mu. I'm just gonna write mu instead of mu k. Is that okay? Times n, which is this, mg sine theta minus mr theta dot squared. That's n. And then I have minus mg cosine theta equals, and then I have m, that term 0, and I have r theta double dot. So that's my equation from the Fnet theta and the Fnet r, combining them together. So let's go ahead. I want to solve for theta double dot. So let's solve this for theta double dot. Theta double dot. So I just divide both sides by mr. So I'm going to put this as in separate terms. Mu g over r, the mass canceled, sine theta. And then I have minus mu theta dot squared, right, because the mr canceled. And then I have minus g over r, the mass canceled, cosine theta. That's theta double dot. And now I have a differential equation, and that is the differential equation that I want to use. And how do I model the motion of this? So let's say that I have my block up here, and it starts with some velocity v. You know, my marker is getting bad, which is kind of amazing that it's lasted this long. New marker. Okay. So it has some velocity v. So that means that it has some theta dot. So I can say theta dot initial, I'll call it 1, is going to be equal to v1 over r. That's the initial velocity. I need that. And then I'm going to say my initial theta, I'm going to say theta 1 is equal to 0 radians. So I'm going to start, no, I'm sorry, pi over 2. And this is wrong too, because remember, that's increasing theta. This is actually negative v1 over r, because I want it to go in the negative theta direction. So I'm going to start at the top of the curve and go down. So I need those two things. If I have theta, now what I want to do is to break this into a time step. Delta t is 0.001 seconds, let's say. So if I break this into a bunch of small time steps, during that time step, I can assume that theta double dot's constant. It's not, right? Because theta changes and theta dot changes, but let's assume it is. If that's the case, I can say theta double dot is equal to delta theta dot over delta t. And that's going to be theta 2 dot minus theta 1 dot over delta t. So theta 1 dot is the beginning theta. Theta 2 dot is the theta dot at the end of the time interval. I can solve this for theta 2 dot, and I get multiply by delta t, add theta 1 dot plus theta double dot delta t. So now I have the velocity, the angular velocity at the end. Now I can do the same thing by assuming this velocity is constant, which it's not. But it's kind of, the smaller I make my time interval, the better that is. So I get theta 2 dot is equal to the change in theta with respect to time. So I get the same idea. Theta 2 is theta 1 plus theta 2 dot delta t. So here's the plan. 1, calculate theta double dot, because I know all these values to start off with. 2, calculate theta 2 dot at the end of the time interval. And then 3, calculate theta at the end of the time interval. Now I just do it for the next time interval. And I can keep doing this process until I get down here to theta is equal to 0. And so we're going to do that. And that we're assuming that it stays on the thing the whole time, which it doesn't. Okay. Now let me point out a couple things. We do need some values, right? Let's say I'm going to pick a mass. It's a person. It's a heavy person, I guess. 100 kilograms. I'd just like to use 100. The coefficient of kinetic friction I'm going to put as 0.1. The initial velocity, v1, is 3 meters per second. And the radius is 3 meters. I just picked some stuff. And then theta 1 is pi over 2. Okay. If I start with the 0 velocity and theta 1 is pi over 2, you'll see here that if I put pi over 2 here, this is 0. Theta dot would be 0. This would be not 0, but this would be 0. But this is the coefficient of friction if it's moving. But if it's not moving, that term would actually be gone. So it would just stay at the top, which is what you would expect. So you got to give it some initial velocity to move it off the side. Let's do this in Python and just go from there. And I'll come back to the paper in a second because there's a whole bunch of awesome stuff in this problem. Whole bunch of awesome stuff. We're going to model both the motion of this going down and when it leaves. But right now we're making it stay on the surface. So here I'm using GlowScript VPython, Web VPython. And in Trinket, I'm going to give you the code. I always give you the code. That's what I do. Let's go ahead and we're going to make a graph. G1 equals graph x title equals x in meters. I'm going to plot a trajectory. Y title equals y in meters. And I did this before. I'm going to say width equals 400, height equals 400. Because I want to plot a x versus y trajectory so we can see the thing moving down. And now we're going to plot a curve, f1 equals g curve, and this will just be tracing x versus y. I didn't write it in the paper, but we'll have to calculate that. And color equals color.blue. Let's put a dot there too. Dot equals true. Okay, now I'm going to put in my variables. So I have r equals 3, v equals 3, m equals 100, g equals 9.8. So g is the magnitude. I didn't use the vector g. This is not a vector-based problem, so I don't need to put that in there. Mu equals 0.1. What else? And now I need my initial conditions. Theta equals pi over 2. Theta dot, the initial velocity, I'm going to write that as theta dot. It's going to be my, let's say it's negative v over r. Make sure it's negative. If it's not negative, it's going to go that way. It's going to really mess things up. Now I need my time. T equals 0. dt equals 0.001. Okay, I think we're ready. Let's make our loop. So I'm going to say while theta is greater than 0. Because remember, it starts off at pi over 2, and we're going to decrease it, hopefully. Let's go ahead and put this in real time. So I'll say rate 1,000. So this says don't do more than 1,000 loops per second, which is nice because my time step is 1/1000th of a second, so run in real time. Now the first thing I'm going to do is to calculate theta double dot. So theta d dot, I'm going to call it d dot, and it's just, I'm going to type in I'm looking at my paper right here. See, I still have the paper. I'm going to type in my equation for theta double dot. So I have theta double dot equals mu times g over r times sine of theta minus mu times theta dot squared minus g over r times cosine theta. Just checking, thinking, mu, I think that's right. Okay. Now I can use that to update theta dot. Theta dot equals theta dot plus theta double dot times dt. So this is an update statement. That's why we don't have to put these indices on there. It just takes whatever the value of theta was, adds this stuff to it, and then makes that the new theta dot. So it's done. I'm done. I don't need to do theta 1, theta 2, theta 3. It just keeps changing it. Now theta equals, update theta equals theta plus theta dot times dt. And you'll notice, that's right, you'll notice that this is, I calculate theta dot first, and then I update theta. So this is technically the theta dot at the end of the time interval, just like I said before. And it turns out that the order of these calculations does matter. This is the best order. So now what I'm going to do is to calculate my x and my y position, because I'm going to plot x versus y. So let's say x equals r times cosine theta, just converting from polar coordinates. Y equals r times sine theta. And now I can plot those. So f1 dot plot xy, and then I'm going to increase my time. T equals t plus dt. And let's see if this actually works. Surprisingly, it does. Okay, so, but you'll notice that it stayed on a circular path the whole time, and that actually wouldn't happen. Let me make another plot of the magnitude of the normal force as a function of the angle theta. I guess I'll make it another graph, because what's going to happen at some point, that normal force pushes away from the curve, and then at some point it's going to have to pull the thing in. And if you have a block on a surface, it can't pull it in, so that won't happen. But I'm going to plot it anyway. If this was a bead on a wire, then you could pull it in. So let's make a second graph. So I'll say down here, G2 equals graph, x title equals, let's plot n as a function of theta. N in newtons, which looks weird. And then the y, no, that'll be theta. Let's just change this to y. And then the x title is theta. And let's do it in degrees. I like to think about things in degrees because I have trouble picturing in the other way. And then we'll say the width, let's put the same 400, but the height, let's put it as 200. So it's a graph, it's not a trajectory. 200 equals. Okay, now I need, let's call this Fn is G curve. I'm going to make it blue too because I don't really care. Color equals color.blue. And then down here, what I need to do is to calculate n. So there's my theta. Now I wrote down that n equation. I'm going to calculate n. So I'm going to say, let's just do it up here at the top. Top or bottom? Doesn't really matter. Let's just do it up here. N equals m times g. It does depend on the mass. The magnitude depends on the mass. When it switches, it does not. So I do need that mass. M times g times sine of theta minus m times r times theta dot squared. That's n. So now down here, let's plot that. Fn dot plot. My x coordinate is going to be theta, but I want it in degrees. So I can say theta times 180 divided by pi, and then n. Let's see what happens. I'd never saved this. Block, sliding, down, curve with friction. Okay, now run it. So this looks weird, but it's not. Okay. This looks weird. It looks like, oh, that starts off with a negative theta. No, remember we started up here at theta is pi over 2. So we're sliding down, and then right here, right there at 48 degrees, the normal force switches from pushing away to pulling it towards. Now, in a real situation, we wouldn't have that. So now we need to model what happens after it leaves the surface, because it's going to leave the surface. Okay. So once it leaves the surface, there's two things that are different. Number one, there's no more normal force or friction. So that's two things. Two, now I have an acceleration in both the theta hat and r hat direction. So let's switch back over to the paper and write the equation of motion for both r double dot and theta double dot for after it leaves the surface, because I want to plot that whole situation. Okay, so let's go back over here to the paper. Okay. Getting a piece of paper, sorry. So here we are, like this. Here's our curve, but we're over here. We've left the surface. So we still have a variable r, and we still have a theta. So what forces are acting on it? Just that mg, and this is the angle theta 2. So now we can say F net r is going to be equal to just the component of the gravitational force in the r direction, which is going to be negative mg sine of theta, just like before. We had that before. But now it's going to be equal to this. It's going to be equal to m r double dot minus r theta dot squared. That's the acceleration in the r direction. Okay, so the mass cancels. That's pretty nice. We know mass cancels. This is projectile motion in polar coordinates. Now, what do I want to do? I actually want to solve for r double dot. So I'm going to add r theta dot to both sides, theta dot squared to both sides. I get r double dot equals r theta dot squared, and that's minus g sine theta. So that's my equation for r double dot. It's a differential equation. Now let's do the same thing for f theta. So f net theta is going to be equal to negative mg cosine theta, right? It's just this component of the force. And that's going to be equal to this whole thing, mass times 2 r dot theta dot plus r theta double dot. Again, the mass cancels. But now I want to solve this for theta double dot. So I can add this term to both sides, or subtract that from both sides. I get r theta double dot equals negative g cosine theta minus 2 r dot theta dot, and divide by r. Theta double dot equals negative g over r. That's a lowercase r. Cosine theta minus 2 r dot theta dot over r. That's important. So now I have a new expression for theta double dot. They have to, but after I calculate theta double dot, that's fine, right? It doesn't matter. I still use my same thing, theta 2 dot equals theta 1 dot plus theta double dot delta t. I still use theta 2 equals theta 1 plus theta 2 dot delta t. Doesn't matter how I did that. And the same thing's true up here. Here's my differential equation for r. Now I need to do the same thing over here. So I need to calculate r double dot. r2 dot equals r1 dot plus r double dot delta t. And then r2 equals r1 plus r2 dot delta t. So I'm going to have two sets of equations, just like you would with an x and y, but here we're dealing with r and theta. So let's go ahead and model this in Python. So I'm going to do a couple things. Number one, I'm going to just draw this path. Okay, I'm going to draw that curve just so that I have some, so I can see when it leaves. Two, I'm going to model the motion until n is no longer positive. And then after that, I'll switch to these equations until theta is greater than 0. And then we can see the motion of the object in the thing. So let's switch over here to the computer. Okay, so here we are, going back to the code. So the first thing I want to do is to make this, I'm going to make a curve, just a baseline curve. So go up here. I'm going to add it in this F1. Technically, when you make curves with more than one graph, you should say which graph it goes with. But if you do it in this order, you'll figure it out for its own. So let's say FC for curve is G curve color equals color dot green. And then what I'm going to do over here, I'm going to start at theta's pi over 2. And I'm just going to change theta and move down to the bottom. So I'll reset it. So let's say while theta is greater than 0, do the following. calculate x and y. Oh, I need a d theta. Let's put d theta equals 0.001. I don't know. Let's pick something. I'm not going to worry about the rate. I just want to do this fast. So calculate x and y. X equals r times cosine theta. And then y equals r times sine theta. And now I need to change my theta. So I'm going to say theta equals theta minus d theta. And then I need to plot this first. So let's say fc dot plot x, y. And then down here, I'm going to say theta equals pi over 2. So I'm going to move back to theta as pi over 2. So that just makes that graph. Let's just run that and see if it works. Because sometimes it doesn't work. You never know. Okay, so that worked. Okay, now you see my bead stuck on the track because I told it to. So I'm going to go over here, and I'm going to say, instead of while theta is greater than 0, I'm going to say while n is greater than 0. Now, if I run this, it's going to be an error because I can't get to line 27. I don't know what n is. I never calculated it yet. So I'm just going to copy this, and let's just calculate it first up here. And then when I do calculate, it's going to change. So I'm doing while theta is greater than 0. This should run and stop when it leaves the surface. Let's just see if that does indeed do that. Yeah, so that's where it left the surface. Okay, now I can go over here and make another loop. And I can say while theta is greater than 0, rate 1000, same thing. Now I'm going to have my new value, my new calculation for theta double dot using my new equation. So I have theta double dot equals, I'm looking at my equation, negative g over r. Now, I do need to go up here and say r equals r, right? Because I'm going to be changing the value of r. I also need to have an r dot because right when it leaves the surface, it's not moving radially. So I'm going to say r dot equals 0. I need those initial conditions. Because here's my r right there. Times cosine theta minus 2 times r dot times theta dot divided by r. Now I can calculate my r double dot. R d dot equals, again, looking at my equation on my paper, I have r times theta dot squared minus g times sine of theta. Okay, so now I can update, put some spaces here. Now I can update theta dot equals theta dot. I could just copy the code. Actually, let's copy the code. Why redo things? So all this stuff I need to copy right there. But I also need to change this to lowercase r, and then I need to update r. R dot equals r dot plus r dot d dot times gt, and r equals r plus r dot times gt, and that should do it. Okay, let's see. I'm feeling a little unsteady right now. I'm feeling a little unsure of myself. That happens. You can make mistakes. Making mistakes is part of programming and doing these calculations. Oh, it worked. Ha! Did it. Okay, so there you go. Now, we can do a couple things. We could say, okay, what if there's no friction? I can easily convert to the problem where there's no friction. And if I do that, that's a classic problem. And you know the answer, where you can look up the answer. I'm not going to do it. Now, if friction is too high, I'm going to warn you. If friction is too high such that the mass stops at some point, then the friction force is still going to be there, and I didn't program in what to do if it stops. And this would just make it move back up because there's that constant friction force, which is a little weird. So it's not a perfect program, but it does work, and I do like seeing this, how the thing leaves the surface. And I'm going to stop there. Like I said, I'm going to give you the code. Let's see if I save it. I'm going to give you a link to the downward, the other path, where it's like an upward curving slide. And then my derivation of the acceleration and polar coordinates, even though I want to redo that. And that's that. So I hope that's helpful. I'll talk to you later.